This is a video to help you with a data analysis for the latent heat of fusion of ice experiment. In part 1, please click on the box to upload a picture of the apparatus that you used. Please include your coffee container or coffee cup, your thermometer, and your weighing scales in the picture. I want to recap some of the theory behind the analysis of the data. The theory relates to a calorimetry problem, which is where we have two components of a system that are initially at different temperatures and then eventually they reach a thermal equilibrium. The two components we have are ice and warm water. Ice undergoes a phase transition as it warms up. The ice at 0 degrees centigrade, which is the equilibrium temperature of ice-water mixture. So this is why we let the ice sit initially for a little bit, so that it reaches 0 degrees centigrade. The ice at 0 degrees centigrade first transforms into water at 0 degrees centigrade during its melting step. The energy absorbed, which has been given the symbol E1, is going to equal the mass of the ice. Let m sub I equal the mass of the ice. So the energy absorbed in this step, which we will call E1, is going to equal the mass of the ice multiplied by the latent heat of fusion of ice. So latent heat is the amount of energy required per gram of ice in order to melt it. Note that when it melts, when given this quantity of energy, its temperature does not change, however its state of matter does. Now the melted ice is now water at 0 degrees centigrade, and that will absorb more energy from the warm water. That quantity of energy we'll call E2 in order to warm to the final equilibrium temperature. And that quantity of energy is equal to Mi multiplied by the heat capacity of water multiplied by the temperature change, which is T sub F minus 0. The heat capacity of water, which I will call C sub W, is equal to 1 calorie per gram. So that is the definition of the calorie. 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree centigrade. So we should put 1 calorie per gram per degree centigrade. Notice that when you buy food, it will have a calorie content label, but that is actually given in kilocalories. You can tell it's kilocalories because they use an uppercase C when they give the units, and 1 kilocalorie is equal to 1,000 calories. And the way you can tell whether the unit is calories or kilocalories is by looking at the case of the C. When the C is lowercase, that's a calorie. When the C is uppercase, that's a kilocalorie. So I just wanted to talk about that so we could relate what we are doing to things that we see in everyday life. The sum of E1 and E2 is the total energy absorbed by the ice as it melts and warms to the final equilibrium temperature from that total energy absorbed from the warm water. As the warm water gives energy to the ice, it cools to the equilibrium temperature. The we can say that the sum of E1 plus E2, which is the energy gained by the ice, must be equal to, if we assume that the heat lost or gained by the system from the coffee mug or the environment is negligible, then if we make that assumption, then E1 plus E2 must equal the energy lost by the warm water. And energy lost by the warm water is going to equal the mass of the warm water, which I will give the symbol M sub W, multiplied by the heat capacity of water. As we want the energy lost, we're going to subtract from the initial temperature the final temperature. This equation, and if we substitute E1 and E2 with these values, will allow us to find the latent heat of fusion of ice. Now let's go to the next page and enter in our data. And I will enter the data that I obtained from the experiment of which I made a video of. So, in my case, the mass of the empty coffee cup was 374 grams. The mass of the coffee cup and the warm water, which was the room temperature water that I placed into it, was 513. If we subtract 374 from 513, we get the mass of the warm water. So 513 minus 374 gives me my answer, which is 139 grams. So the mass of my warm water, given the symbol MW, was 139 grams. My initial temperature was 72 degrees Fahrenheit. In the next line, I want to convert that into centigrade. To do that, we take the temperature in Fahrenheit and subtract from that 32 and divide that result by 1.8, and that gives us the temperature in centigrade. When I do that calculation, I get 22.2. The final temperature of the water at equilibrium was found to be 60 degrees Fahrenheit. You can see that the warm water cooled slightly. Let's convert that number as well into centigrade. So I'm going to subtract 32 and divide by 1.8, and that gives me 15.6. So in centigrade, my initial temperature was 22.2, and my final temperature, the equilibrium temperature, was 15.6. At the end of the experiment, the mass of the coffee cup with the water and the melted ice was equal to 525 grams. To determine the mass of the ice added, we subtract from this number the mass of the coffee cup and the warm water, which is 513. So 525 minus 513 is equal to 12 grams. So the mass of ice I must have placed into the coffee cup must have been 12 grams. Now let's calculate the energy lost by the warm water to the ice. That is equal to the mass of the water, which was given, we calculate that up here in step C, which was 139 grams. and we want to multiply that by the temperature difference in centigrade. So my initial temperature in centigrade was 22.2 and my final temperature in centigrade was 15.6. So the energy loss by the warm water to the ice was equal to 917 calories. Now let's calculate the energy gain by melted ice to warm to the final temperature. This is the quantity E2 in the diagram that we just discussed. So that's equal to the mass of the ice, which was equal to 12 grams, multiplied by the final temperature, which was 15.6. You see we're just subtracting 0 from that. I didn't put that subtraction 0, there's no need to. So if we multiply 12 by 15.6, we get 187.2. Hence, the energy that was absorbed by the ice during the melting step must be the difference between these two quantities. So 9 over here, 917 minus 187.2 gives me 730 calories. If I divide now this quantity, which is the energy absorbed by the ice during the melting step, by the mass of the ice, which was 12 grams, I get my estimate for the latent heat of fusion of ice from my experiment, and I got 61 calories per gram. Please perform these calculations for each of your repeated data runs. Once you have done that, let me just scroll to the end here. Once you have done that, please summarize your results. And calculate the average of your results here. The average is equal to the sum. So in my case that would be 61 plus 65 plus 70. Add those together and divide by the number of data points, which is 3. And that will give you your average. Note that the accepted value for the latent heat of fusion of ice is 79.4 calories per gram. Compare your average result to the accepted value and comment on the success of your experiment. You can type your response in the box below. And that's the end of the analysis.